Hello, thanks for joining us today for our webinar on encrypted traffic analysis. Detect, Don't Decrypt, Part 1. We'll be presenting Part 2 of this series soon, which will present deeper insights into the topic. Today's presenter is our co-founder and chief scientist, Gary Cullum. And Gary's going to provide us some insights into the issues that are presented to the security professionals out there in terms of being able to analyze and determine what is happening with encrypted traffic attacks. So with that, I'm going to jump over and turn this over to Gary. So Gary, over to you.
All right, so a lot to talk about today. I'm just going to kind of jump into it here. I guess quick background or introduction. So I'm Gary. I'm one of the co-founders here at Awake. Prior to Awake, I was the first employee at Silence, focused on executable disassembly and feature extraction for machine learning, for threat detection. Prior to Silence, I was at NetWitness RSA. So, really kind of ushered in, I think, the era of network forensics, that company did. Was honored to be there, part of that. Came into NetWitness via acquisition, started a company called Preventure, and we developed basically what would be considered EDR nowadays, although we didn't have that really cool term back then. If we go far enough back, I kind of got my start in the industry working on the Dragon IDS, if anybody happens to remember that blast from the past. So I've kind of flip-flopped back and forth between network and endpoint each time I've made a move. And even roles within those companies have kind of flip-flopped back and forth between research and development and professional services around incident engagement and incident management, stuff like that. Because, hey, if you're going to be a researcher, you can, do your research in the lab, which is maybe not so optimal, or you could, go out into the front lines where you're investigating breaches that are cutting through the current state-of-the-art security stacks and analyze what's going out there in the real world. All right, so we're gonna go ahead and just kind of jump into this here. As soon as I learn how to use PowerPoint and advanced slides. All right, so we're gonna be talking here in this particular presentation. As Bill mentioned at the beginning, this is part one of a two-part series. This one's a bit higher level, and Troy will be presenting next week and doing a really deep dive into packets and TLS and the techniques that are available for doing analysis. But just by way of sort of summary introduction of why we're even talking about this stuff in the first place. One thing to know is that at Awake, we've been doing encrypted traffic analysis since the formation of the company. So in our very, very first prototype that went out the door, even early as 2015, those versions of the system and platform were built around encrypted traffic analysis. So when we formed the company, at that time, encrypted traffic TLS was a much smaller, surprisingly small percentage of network traffic. But of course, the writing was on the wall, and we knew that was, that was something that we needed to address to be a powerful and relevant network detection and response platform moving forward. And so, we've been doing this for a while, not just researching it, but actually utilizing these approaches that I'll be talking about out in the real world for quite some time now. And we've been in the industry a little. We've kind of gotten out there and sort of talked about some of our research and findings. We're going to be doing that a lot more now, and even in these next two sessions and Troy sessions next week, we're going to be kind of we're pulling the curtain back and showing you a lot more information about what we've learned over the past 5+ years doing this. But there's even some check-ins along the way. Back in 2018, gave a presentation on sort of issues with kind of industry standard approaches, and then we'll be updating and building on those in this session. But really, I think a summary point, if you take away anything from what we're going to be talking about here, and this is the point that kind of surprises people and really drove us to put these presentations and this information together, and that is, on any given week, and there's this is an average, so sometimes more, sometimes less, but on average, we're finding that about half of the breaches that we end up reporting customers or compromises we detect are detected because the attacker has used TLS, because the attacker has used encryption. So it's, it's really important. And basically what we're getting at here is that TLS is not leaving us helpless and hopeless, when it comes to network traffic analytics and very specifically threat detection. In fact, we're finding that TLS has been extraordinarily helpful for us, and so we'll be dissecting that a bit as we go through this. So really, important points here are, you may hear these kind of claims that unencrypted traffic, is equal to complete visibility. And when it comes to threat detection, we're finding that that's actually false. In a lot of cases, actually, the inverse of that is true. And so, yes, it is true that, of course, encrypted traffic does break some detection methodologies, maybe what we could call, simple detection methodologies. But again, the really, the important kind of asterisk here is this is in the context of threat detection. So everything we're going to be talking about in these presentations is around detecting threats, detecting, malware and backdoors and remote access of various types. And there's an exception to that, right? And that's DLP, or data loss prevention. In the data loss prevention use cases, of course, you can't do data loss protection and encrypted traffic analytics together. Data loss prevention, which looks at the content of data and looks for social security numbers or credit card numbers or addresses or whatever the case may be, or even very sophisticated topic modeling of content, trying to determine if sensitive data is being discussed. You need the content for that, but but here we're kind of focused on what about the threats, what about the breaches and the compromises? Does the same apply? And as we'll see, the answer is absolutely not. And one other point, I'll kind of touch on this as we go throughout this. Encrypted traffic analytics has been unbelievably powerful. We've been very surprised by what it's done for us over the years. But we need to, of course, keep this in context. It like any detection methodology, they all have their pros and cons, and they're most effective when you put them all together, right? So I use this term forensic detection to describe what human beings tend to do, what we do in an investigation, and that is we take very different types of data points, and we take those data points, those different types of data points over time, and we assess those and make determinations from that data. And the same applies here to automated forensic detection. It's taking different types of data and taking that data over time and making assessments of it. And of course, in the automated sense is what we're interested in. What can we detect automatically? Okay, I guess one other little contextual point here is what is the kind of one of the big underlying questions we're trying to answer here in this particular presentation, this part one, and that is, look, if you have to choose between decrypting traffic and doing your analysis and threat detection on the decrypted strings, or not decrypting the traffic and doing encrypted traffic analytics instead, which one should you choose? Now, of course, if you have the budget and you have the legal approval, which we'll touch on in a minute, it's extremely important to make sure that you see why when it comes to doing decryption. But if you have the approval and you have the budget and you have the resources to both analyze decrypted traffic as well as the encrypted traffic, the pre-decryption of the traffic simultaneously, absolutely do that, right? Best of both worlds. But if you have to pick between one or the other, which one of those two is better? And as it turns out, as we'll cover here, we have found that actually the encrypted traffic analysis tends to be better. All right, so let's kind of get a sense for the landscape out there. Right? When we talk about encrypted traffic analysis, there's a scope of strategies that are available to enterprises these days for dealing with encrypted traffic and doing analysis and doing threat detection. So let's just kind of, sort of lay those out here. And so on one end of the spectrum, we have just straight decryption, taking the traffic, cracking it open, decrypting it, and doing analysis of what's inside. And in that category, under that category, one approach, and this is kind of the most common one people tend to think about when the subject comes up, is full interception. Taking all the traffic and decrypting, just automatically decrypting all of it, or as much as can possibly be decrypted, based on sometimes there's technical limitations, touch on a little bit here, but decrypting as much as possible and just doing blanket analysis across all of it. This is the one that, again, if you have to make a choice between one or the other, some red flags to watch out for. There's a number of discussions out there around security concerns around doing that. Definitely do some read on that. But I think the bigger issue that we tend to find people causes people to pause a little bit more is the legal issues around it. And so there are a lot of still unanswered legal questions around doing full interception and decryption. Like we see here, kind of discussion about consumer privacy protection laws that states like California and other states are starting to follow suit, and we're seeing out of the European Union and other places. According to analysis out there, there are some really big kind of questions around even the legality of it in the first place. And this is not even taking consideration wiretap considerations and stuff like that. And so that's why we say when we talk about doing interception, make sure that you have your bases covered, that you've kind of covered all sides, all sides there, and make sure that you have legal approval, kind of counsel behind you if you're going to take this approach. Along those lines, we start to get into that. Sometimes what comes up in conversations, and I've seen this in other presentations, especially from vendors that actually sell technology for doing decryption. They kind of address that with the, well, wait, look how common it is, right? If there were that many questions around it, it wouldn't be that common. And the type of graphs that we see referenced to make those cases are like this one, that we have from Cloudflare. And what this graph is trying to tell us is that for any given day, and here we see August 11th, for any given day, and in this particular case, August 11th, 25% of the traffic that Cloudflare received was intercepted and decrypted before they received it, right? Which seems to make the case, wow, that is like stunningly common. That is a huge percentage of organizations, and 1/4 of internet traffic, right? It takes a stunning number of organizations to be able to do that if Cloudflare sees those types of numbers. But what we found is that this interpretation of the data is actually not consistent with measurements that we've taken over time. And so, look, one of the things that we're in the business of is looking at network traffic and abstracting what's happening on the network into devices, and then tracking and analyzing those devices over time, and automating the analysis and investigation of devices. And so a big part of that is that we're constantly trying to answer questions for analysts and investigators. What is on this device? What is this device, and what's on it? What's running? What software is on there? What's interesting about it? How's it deviating from other systems? These really core kind of common questions. And it turns out that behind, when we look under the hood of graphs like this, what they're doing is they're using user agent for ground truth. And so there's organizations like Cloudflare that are doing this type of analysis where they terminate the TLS session, and so they can extract the fingerprint. We'll talk about that in a moment, but they extract the TLS fingerprint, and then they say, okay, this fingerprint belongs to this browser. Now let me look at the user agent, see if these things match up. And if they don't match up, well, then we can derive that the session has been intercepted, that there's something in the middle that has re-encapsulated the request in a different, a TLS with a different fingerprint. And you know what? I wish that user agents could be that accurate. Again, as I mentioned, we're kind of in the business of monitoring devices over long periods of time and reporting, to users of the system what software is running on there. So of course, user agents would be fantastically useful, make our lives so much easier if we could believe and trust those. But what we found over time is that this absolutely is not the case. That if you monitor devices over time and you build a profile of software that's running on the devices based on user agents, that especially for workstations and kind of the most common type of devices we're talking about in these scenarios, you get wildly inaccurate representations of the software on there. And so there are a huge variety of cases why user agents don't match up, they're not the true reporting of the software to label for the software that's making that request. Not the least of which are things like if you just do a Google search right now for best Google Chrome extensions, you'll come up with all kinds of blogs, many of them in their top 10 lists, list things like user agent switcher, which is published by Google, over 1 million users, and we see over 2,000 high rated reviews, which for a Chrome extension are very big numbers. So this is common, right? This is common intentionally because users users are switching things up. It's common because software just modifies and copies headers, and so here we get facepalm kind of Godzilla in looking at data like this. All right, so full interception, right? There's a lot of questions around it. Again, if you can get the approval to do it, there are a variety of reasons to do it, but there are also a lot of issues to be aware of and make sure that you're addressing those before you go into it. So another approach under decryption is what we call surgical interception. So as opposed to full interception, surgical interception would be, you have done some sort of analysis, or there have been some type of, triggers of either alerts or, behavioral kind of triggers or whatever the case may be. But we've gone from all the traffic now down to just a small number of sessions that are interesting. And so that's just taking very specific sessions and decrypting those. And of course, there are a variety of cases we've come across where that's very useful and helpful. This is something that we definitely not only encourage people to do, but there are a variety of scenarios where you kind of need to do it. But it's based on probable cause, right? So you're working with a much more restricted data set, and it tends to address some of the concerns that we see around full interception. The really, really, really good news here, though, is that this is really a lot more of a commodity capability, meaning that there's an enormous amount of software out there that supports these workflows. I mean, even Wireshark has capabilities to do these types of workflows. So lots of tools available to help with what we call surgical interception. All right, so that's decryption. Now, what if we don't decrypt? What if we just leave the traffic as is and do encrypted traffic analytics? So I'm just going to kind of address sort of both of these together. There's I think the most well-known approach to encrypted traffic analytics out there right now is JA3. But there's also another, Cisco Mercury, and they're both very different from each other, but they also, in a very important way, have a similarity. And so the difference between the two is that JA3 ultimately is creating hashes, a hash database, this database full of hashes, and those hashes are created from certain fields in the as TLS is set up, right? TLS session, TLS handshake. And then those hashes are in the database are matched to software, right? So the database might say Chrome, and these versions of Chrome have this JA3 fingerprint, which is really just kind of a a collection of hashes of certain fields in the TLS handshake, and that's how it can take a TLS session and come back and say, hey, I think this is Chrome. Right. Cisco Mercury doesn't, isn't using the hash approach. Instead, Cisco Mercury is collecting many more fields and actually just collecting kind of the raw data and building a database out of that. And so, when we do an analysis, and again, we have some presentations that get much deeper into assessment of the accuracy of these approaches. And there'll be a little bit of updated information in Troy's presentation next week on that, right? And so there's there are big differences between Mercury and J3. But the thing they have in common is that they're both databases, right? And so they both require work up front to create a fingerprint, however that fingerprint is represented by each of them, and that may change over time. But there's ultimately a fingerprint that is matched to a piece of software, right? And so, so what we find actually with these approaches, and again, you'll see this in a lot more detail next week, but those fingerprints are have a very limited shelf life in a lot of cases. And so, when the fingerprint is created, it may match to that particular piece of software, at the time it was created. But we actually have two problems that emerge when using these approaches. One is that the fingerprint expires, the software changes over time, which is a lot more obvious. But the bigger problem is, as time goes on, we tend to see that fingerprint migrate to other pieces of software that start using similar shared libraries and invoking them the same way and setting up sessions the same way, perhaps. And so, so both of these are this database approach, and they both kind of have the issues that we tend to see with with what we could call sort of pattern-based approaches to looking for trying to identify what a session is, doing this encrypted traffic analytics. Now, there's a way, and I'm going to show you what we do in more detail here, so it's not so abstract on this slide. But maybe for the point in this conversation, at this point in the conversation, I think the most relevant or best way to compare and contrast is that we are not using a database. We're not pre-populating a database of fingerprints, and we're saying that this piece of software or this fingerprint belongs to this specific piece of software, and now we're kind of in this hamster wheel of having to keep up with creating new fingerprints all the time and prune the old ones and update the old ones and all that stuff. Instead, we're taking a machine learning approach. And look, I'll be honest, every time I am on a presentation and I hear somebody say machine learning, I absolutely roll my eyes, and the finger starts getting closer to the disconnect button. I wish I had a different way of describing this, but that's exactly, it's precisely what we're doing here. And so what we're ultimately doing is using algorithms to analyze the traffic over time and traffic from devices over time, and start to assess what is normal or abnormal or common or uncommon for particular uses of TLS. And I'll show you some really neat examples of how that manifests, from a detection perspective. But again, right, the really important thing to understand here is, why are you doing TLS analytics in the first place? Is it to be able to look at a session and say, hey, I know that this is Chrome and it's this version of Chrome? Or are we doing this because we're trying to figure out, hey, this looks like a potential threat. This looks like a potential risk that should be investigated. And in the latter scenario, we find that this is a far more scalable approach. There's one other approach, so I'll just make a mention here. We're not going to touch on it too much here in this presentation. I do expect, this is not a commodity capability right now, but I expect within the next couple of years that any technology that does network traffic analytics of any type will probably have tunnel modeling approaches or methodologies as a feature, which is to say, they'll look at the traffic and they'll try to tell you, hey, in this TLS session, I think inside is an RDP session, or it's an interactive, command line, remote shell type session, or whatever the case may be, by using supervised machine learning models to ultimately identify those things. And they're useful in the cases where it works. Like I said, I think that this will be a pretty standard thing, and the effectiveness that we've seen, especially when it comes to threat detection, is can be quite limited with that. All right. So before we get into exactly, kind of how an example of how this works in a way currently, there is one sort of prerequisite topic to address here, and that is understanding what you're looking at over time, right? So it is extraordinarily common for, especially workstation like laptops, in an enterprise, to have a half dozen different IP addresses on them in a single day, or a single IP address, in a conference room or common areas, to have a half dozen different devices on them in a single day, and it could be Windows 1 hour and Android the next hour, whatever the case may be, right? And so if you're going to do analytics on network traffic, and you're going to try to assess what is normal, what is abnormal, what is common, what's uncommon, what are patterns of behavior over time. Imagine a beacon coming from a device once per week, right? Which is very, very common that we encounter, especially in the malicious scenarios. And so, you come across this, you have that beacon that's occurring, but look, every single day that device has a new IP address, and that's what we see here, right? And so one of the things that Awake is doing is from the edge of the network. So we are a full packet capture system. So sitting at the edge of the network, right? Major ingress, egress point between the enterprise, or demarcation point between geographical locations, where we sit there, we collect, we record all the traffic. So that's full packet capture does, and then all the analytics we do ride on top of that. So we're not importing, we don't need to integrate with various log sources and all these other integrations required to work and be effective. We assume that we're just going to get traffic from network edges, and all our ability to do analysis is going to be on that kind of profile of traffic. And so we create a fingerprint of devices. We do this, the analytics on the device or on the traffic, create fingerprints of devices, and then we tell you where a device has been as it moves around the network. We tell you what IP addresses it's had and when it's had those IP addresses. And we're looking at an example here where we see this device had this particular IP address for about an hour, and we see that every day it moves around to different IP addresses, right? So again, when we think about doing the type of analysis, or if you start kind of asking yourself this question, like, all right, if this is so effective, why am I not seeing it elsewhere? This is a prerequisite problem that has to be solved, and that we've seen to date. It hasn't been solved outside of our platform, but by solving this, and again, this was something that we had even in those early prototypes, and definitely in 1.0 of the system. This is what's allowed us to do the type of encrypted traffic analysis that we've done, over the years, because we do have this implicit sense of a device over time, where IP addresses are really just an abstraction. A device is a collection of IP addresses and time frames. All right, so what can we do with that over time? Here we're going to start looking at a much more specific example. And so we have the adversarial modeling language, what we call AML. And this is a very, very simple example here. We're not going to get into too much AML in this particular presentation, but I did want to give at least one example, one very, very common example that we use. And what this is showing, and so as it mentions here, right, kind of the neat thing about AML is it allows you to create definitions or models of behavior using machine learning, but in this format that is very familiar to a lot of people. So you might not look at this and understand exactly what these predicates are saying, but the syntax is very similar to Splunk, very similar to Wireshark. And so once you kind of learn a handful of the basic and very common predicates, using the language becomes very easy. And what's cool is you can look for the types of things that even machine learning on its own has difficulty doing. But because we have this language that exposes the ML engines underneath, you can kind of take the bits and pieces of the analysis that work well together, fit well together, and create definitions of behavior like you see here. And of course, it's open, so you can come in and copy these and learn from, all the models that we ship with are open, so you can, come in and do analysis and learn from them and copy them, extend them, and, create your own similar kind of models. But all right, getting back to this one. So what we have here is this one, we see device.characteristic. So we're looking at something equal to something else, right? But at the beginning, device.characteristic is saying, it's getting back to what I was talking about with that fingerprinting, right? We're asking the analytics engines underneath. We're saying, look, I don't know I don't have a pre-existing definition for a TLS fingerprint, but the analytics, you've been going over all the traffic. Give me devices who have software running on them. They're creating traffic, putting traffic on the network, where the TLS fingerprint is, in this case, relatively uncommon for similar devices, okay? So this is not the same as saying this is uncommon in the network, period, right? But the analytics are comparing devices that are kind of similar to each other. It doesn't make sense to compare an Android device to a Windows device, or a Mac to a printer, or things like that. All right, so we're saying, show us the devices who seem to be running some type of software that's a little bit abnormal for similar types of devices. And we're pairing that up. So that top line is the TLS, talking about the, that part of the TLS fingerprint. And we're saying, and, we want those sessions to also be going to a network that is relatively uncommon for, this type of traffic, right? And then the final part of this is, for it to be a characteristic artifact in the first place, there should be some degree of recurrence. This should be happening, whether it's once every 24 hours, or once every few days, or once every minute or hour, whatever the case may be, right? Short periods of time, long periods of time. We want to see some level of recurrence over time. And so what's kind of neat is when we put all this together, the way you can think about this is we're basically creating an application fingerprint based both on characteristics of the traffic, right? Characteristics of the TLS, the way it's set up, as well as we're putting it together with the way that application is being hosted, right? And what's really, really cool about this is, again, we don't need a database. This is dynamically derived and continually updated from all the network traffic. So again, remember, what are we trying to do here? We're trying to find the threats. We're trying to find the bad stuff. And bad stuff tends to stand out either in very, based on very specific fingerprints or behavior over time, right? And that's what we want to get to. So do we have pre-existing, do we have a fingerprint for what Chrome is? No. But is Chrome very common? Yes. And so, just by looking at traffic over a relatively short period of time, we could very quickly tell, okay, this fingerprint is very, very common, and it gets used this way. Right, and so that is not so interesting from a security analyst perspective, right? But this other traffic, it is interesting because it stands out some differently, and so that's basic idea there, right? So what kind of things does this find? This is actually a real example, and so what we have here is we're just showing the screenshot of the NADIQ page, which is the summary level information that we have about devices as we track them over time. This device, obviously Raspberry Pi. I didn't call it, I didn't name it. No one came in here and named this Raspberry Pi. That was automatically, the system automatically derived that by watching this device over time. And we can see actually over there on the far left-hand side, it's been tracking this device for 5 weeks now, or at least 5 weeks at the time this screenshot was taken. And over that period of time, one of the things that have stood out, that have separated this device from other IoT-like devices, is both this TLS traffic. It has this fingerprint that it's not the only one in the network. In fact, there are 4 other devices. There are 4 devices that have this particular fingerprint. But this device is using it recurrently enough, and it's unique enough that it is characteristic of what separates this device from others. Not only that, but this traffic is going to a network, this ASN, that is also noteworthy. Again, it's not the only device in the network that has traffic going to that particular ASN, but the combination of these things, and so we see when we do the math, right, 12% of 58 or 24% of 29, seven instances, 7 activities with these characteristics. And so we have models like the one that I just showed you that puts that information together. So that information is neat to have in the UI. It's very, very helpful for kind of getting your bearings on what is interesting or noteworthy about a particular device on the network. But of course, we have a lot of models that are sitting on the system that are doing analysis of that data for you and surfacing the really interesting results, like this one. And so what we see here when we pivot on this model is we get this device. And we see this very beautiful pattern once every 24 hours, which is why we see it, 7, so 7 per week is what we were looking at there. So we saw 7 instances of it. And we see this device that's beaconing, right? And so when we go in and we look at the traffic, what we ultimately see is that the traffic is going to an IP address that has been labeled realvnc.com. A lot of people may be familiar with passive DNS, right, which is a system that watches DNS requests and responses going back and forth, and just passively creates a database saying, okay, I saw this request and response, so I know that this IP address over here has this particular domain name associated with it. Well, you can do the same thing with most protocols, not just DNS, right? TLS has information that allows you to know domain names and server names, HTTP, SMB, the vast majority of protocols on the network. Most of the protocols you can think of have some kind of concept of server name that goes along with them. So by looking across all the protocols, we build actually a very, very detailed and helpful database associating names to IP addresses, which is a very, very useful way to quickly get an understanding of what that server is out there that devices in your network are communicating with. And so in this case, this model that I described just a few moments ago, very, very generic model, we frequently find these like shadow IoT like scenarios like you saw there, and again that was real, it wasn't something we faked in a lab. So we had shadow IoT running a remote desktop, which is I think very concerning for a lot of institutions. And what's to me like the best part about this, the thing that's most exciting for me, especially working with this technology, is it doesn't require us, it's not require anybody to get on that hamster wheel or that treadmill of trying to keep up with a database of signatures about TLS sessions, that this is all dynamically derived, and as the network and as software is updated over time, this same model still works. And it's not just for shadow IoT, but you can very easily imagine how malware on Windows systems and different types of scripts or remote access tools for Mac and other systems, right? You can I think easily imagine how this logic like this easily catches those types of scenarios. And that's right. No conversation would be complete without talking about TLS 1.3. I think we're hearing and seeing more vendors in the network traffic analytics space or network detection response talking about TLS, having a lot more to say about it. And I think what we're seeing is a reactionary response to these frankly sensational headlines. Talking about this, the sky falling TLS is just bringing the smackdown on enterprise monitoring. And the question is, okay, this is great. We can write articles like this or write blog posts like this, but when we get out there and we look at traffic and we actually look at what's on the network, what is the reality out there? And what we see is here's a session actually using using just current version of Chrome, connecting to a server that's designed to test compatibility with TLS 1.3 servers, between client and server. And as I expand this out, we're looking obviously at a Wireshark dump here. We still see that all the information that we were using before, it's still there. But even better than that, even much more useful than that is this may change over time, right? TLS 1.3 actually introduces more extensions, more data points that we can use for fingerprinting. What we found in the real world, the reality is TLS 1.3 is helping us, not hurting us, helping us by helping us create more granular fingerprints for software using the updated extensions or the few updated extensions that we've seen actually kind of make it out into the real world. So instead of facepalm Godzilla, we get a quadruple facepalm for this one. Don't sky's not falling. Okay, so kind of quick review, sort of overview here. This is the default approach we take. I just showed actually in this presentation, this part one of this two-part series. I just showed one technique we use for encrypted traffic analytics. This is by no means the only technique. In fact, we are doing more and have more new things coming out. And Troy will be getting into more details on the other techniques and some of the newer techniques that we've begun using out in deployments. Also, JA3, like I said, it's an industry standard, so of course we support it. I mean, look, going back to forensic detection and making forensic detection effective, making an analyst or investigator effective, the more data points you have, the better. So if you have the hashes, if you want to import and use the hashes, we can totally support that too. The surgical interception, as I mentioned, Awake is a full packet capture system, right? So by default, we record everything, all the traffic, and again, all the analytics we're doing is on top of that packet store. And so, you can go back and do analysis at a later date if needed. Of course, you can export, PCAPs and traffic out. Actually, a really neat feature is I was showing how we track devices as they move across IP addresses over time. If you ask for an export for a device, and that device has 10 different IP addresses, that's fine. You'll get a single PCAP exported with that device's traffic crossing as it moves around between all the IP addresses, and it'll just be concatenated in a chronologically correct order, single PCAP, all the traffic from the one device. But nonetheless, right, very useful, very important for surgical interception type workflows. And look, again, the context, that kind of question that we started out with at the beginning of this is, if you have to choose between one or the other, which one? And there are considerations on both sides that may may influence you one way or the other. But the reality is, if you can do both, fantastic, right? You get the best of both worlds, and if you can do that, we will definitely take that traffic in, ingest that, do analysis of that, and then hey, you get the encrypted traffic analytics on pre-decryption and deep deep packet inspection on decrypted traffic post decryption. All right, so kind of summarizing here. Encrypted traffic analytics is it's not going away. It's something we've been doing for the past 5 years now. Maybe the impact or influence of encrypted traffic on the network hasn't brought the doomsday kind of scenarios that we still frequently see in the headlines, and I'm certain that we will continue to see as time goes on. But it is a very, very useful technique for finding bad stuff. In fact, we find that it can be as effective, and in many, many cases more effective than previous approaches. Also, to do this type of analytics that I'm talking about, again, it requires kind of figuring out what's, to do this continual sort of update on the fly as time's going on, analyzing the data, it takes time, right? So it takes data, right, which typically is synonymous with time. And so to do that, it's basically impossible to separate the subject of encrypted traffic analytics from entity tracking. The type of analysis and analytics you can do, if you can't solve the tracking problem over time, you're basically limited specifically to the database type approaches. You're basically limited to being able to make decisions based on the information you get from individual sessions. And it becomes very, very difficult to make accurate decisions on data points over time, because basically you don't have ground truth. You don't know anymore if you're looking at the same device today versus yesterday versus the day before. And finally, encrypted traffic analytics, as we've been talking about here, incredibly powerful, incredibly useful. It's phenomenal the types of scenarios that we've uncovered, or types of threats we've uncovered using these techniques. But again, everything, kind of understand where everything fits in. It's just one methodology, right? It's one methodology that fits into, I think, a more, a kind of higher level strategic approach that we could refer to as forensic detection, which would be combining many methodologies. There's automated OSM, and we have some presentations and kind of information on what we refer to as AVA, or the Awake Virtual Assistant, which is automating the analysis that an investigator may do on open source intelligence, and bringing that in to help make a decision about what is being examined. Of course, there's the machine learning AI type approaches. We looked at one very specific example here: heuristics, IOCs, right? Rules, signatures. That all of these techniques are valid, and in combination, they're even better, right? And then you can start. They all have their pros, they all have their cons. Put them together, and the pros of each of them can start, basically compensating, filling the gaps of the cons of others. And encrypted traffic analytics is just one of those techniques. All right, so it brings us to the end here. It looks like we got a little bit of time for Q&A. I don't know if I think we saw some questions coming in, but I've been sitting here yapping and talking.
Yeah, hi, Gary. Yeah, Bill here again. We've been kind of, monitoring the questions that people are typing in. So again, for anyone out there, if you do have a question for Gary, please go ahead and type it into the chat window in your Zoom interface. And so, the first question that popped up that seems pretty relevant, it says, I don't understand how you can say more threats are detected by looking at encryption as opposed to having the unencrypted contents of the traffic and being able to examine the data directly. More specifically, why do you say encryption analytics are better than content analysis?
All right, we're coming out swinging today. Yeah, no, you know what? Isn't that question the elephant in the room, right? That's awesome. Awesome question. So yeah, like I said, that is helpful. How we can look at everything we just looked at, but there's that question. How is this better than looking at the unencrypted traffic, or how is it more accurate, right? And so I guess there's two parts to thinking about this. The first is, again, making sure that we're in the same sort of frame of reference here. And that means that we're not talking about data loss prevention. We're not talking about DLP, right? Again, DLP is looking for, social security numbers and credit card numbers and addresses and things like that. To do that, or maybe it's, very sophisticated DLP and it's doing topic modeling on the content, trying to figure out, are we talking about the subjects that are very sensitive to the organization? Yeah, to do that, content is absolutely required. You can't do that on encryption. But the frame of context here that we're focused on here is threat detection again, right? So malware and remote access and the use cases or the scenarios that kind of revolve around those issues. And in a question, so in a question like that, the thing we gotta, it's very subtle, but the thing we gotta recognize is there's actually a really big assumption in there. And that assumption is when we receive, when we, I say we as an industry, of all the kind of the products and technologies and methodologies that are out there in aggregate, right, across these different, sort of markets, whether it's IDS or IPS or network detection and response or network traffic analytics or full packet capture, whatever the case is, right? We put them all together in aggregate. When we take unencrypted, let's take encrypted traffic just off the table as a subject and say everything is unencrypted. When we take that traffic and we send it to these systems, the assumption that's being made I think in a question like that is that those technologies are actually pretty accurate or pretty effective at looking at unencrypted content and making good decisions about, hey, this is bad and this is good. And what we know, I think from at this point decades of experience is that that is false. That is patently false. That it's the web threats and the browser extensions and these things that are constantly cutting through enterprise security stacks like hot knife through butter. You get to see the JavaScript that's inside the session. How effective are our technologies at identifying malicious versus non-malicious JavaScript? And we kind of know the answer. There's a reason that so many APT groups create so much malcode based on those technologies because it's extraordinarily difficult. And we're not just talking about I'm kind of referencing network traffic analytics systems or network analysis systems here, but whether it's EDR or network, there are whole classes of threats that are very difficult to identify accurately. And it's specifically what we're talking about here. When you decrypt in mass and you're just looking at web traffic, and look, we have now decades of consolidation of applications and protocols and things like that into web traffic. There used to be all these different protocols that we'd see across the internet in the late 90s that you just don't see anymore because that functionality has migrated to, to be APIs over HTTP or, wrapped in TLS. And so we have this explosive proliferation of new applications and technologies. And, the funny thing is, I think this dirty secret in the industry is, the challenge is not keeping up with the bad stuff and what the bad actors are doing. The challenge in that perspective is actually keeping up with what's legitimate. The legitimate software is evolving so rapidly that a lot of what you see in the legitimate stuff ends up looking like what malicious used to look like, right? And so so we just find that looking at decrypted traffic for threat detection, except for in some very specific cases where you get these signatures, you get a URL for whatever the malware du jour is of today, and they didn't change the configuration enough, and so we know that's making a request for this directory or has this header element. The signature sort of approach is great. They're fine, but those are the exceptions, and it turns out that the generic ways of modeling behavior over time and kind of coming up with these fingerprints and looking to see what's normal or abnormal for a fingerprint, it catches those scenarios, the more sort of brain dead scenarios, as well as the scenarios that we haven't previously identified. So sorry, I didn't expect that to be such a long and sort of rambling answer there, but that's one, I think, an important way to look at this.
No, I appreciate that, Gary. I mean, clearly this is a topic that a lot of people are looking for more information on. It certainly seems to be up near the cutting edge of what's happening in the industry. Similar in the same vein to that first question, we have another one here from the audience, and this question is, I imagine detection in encrypted traffic would change over time, just like plain text-based detection. So does my team have to manage two completely different sets of detections?
Yes. No, I mean, the answer is no. Yes, I get where the question's coming from.
Yeah.
Ultimately, answer. I'm chuckling about it though, because look, I mean, hey, I can, I can give you the totally non-altruistic answer here, a completely selfish answer, which is we have the same problem. Like, I don't want to be, nobody here, nobody in our threat team wants to be in the business of having to day in and day out create fingerprints for a database of what these different software libraries and applications look like, and continually do that from here to eternity. And so we don't even want to have to manage that type of information, right? That if it's difficult doing it in one enterprise, and it's very difficult doing it across many enterprises. So no, and that's actually why we put so much time into our approach. And we kind of talk about this, I guess, when we tend to focus on other subjects. But one of the things that we're doing that's really unique is we're looking for when anytime anyone talks about normal or abnormal or common or uncommon or stuff like that, there's another elephant in the room around that, and that's baseline. What is the baseline? Ultimately, what are you comparing to determine what is normal and what is abnormal? And what we've seen in kind of all the solutions that are out there is that they look at the device itself. They baseline a device, again, not solving for the IP address changes over time and things like that, but let's benefit of the doubt. Let's kind of take that off the table. They'll baseline the activity of a device, whether we're talking about behavior, whether we're talking about fingerprints, all the same thing here, and then look for changes over time. But as we all know, like, it's going to change over time. And if that device is a user device, if it's a workstation or a desktop or something like that, laptop, depending on what type of projects the person's working on, several times a year. Think about yourself. You probably go through, transitions between major projects yourself. And so your behavior and software you're running, and these things are changing all the time, right? And so the most common approach to baseline that we see is looking at the device and asking the device itself what's normal and abnormal. And we don't do that at all. We never trust the device. We never trust any device to tell us what's normal about itself. So our baseline is the background. And I think I mentioned it earlier. Our background is not the entire network, right? Because again, it doesn't make sense to compare, Windows to a TV or a printer or some IoT device and things like that, right? So instead, of course, because we have to create these fingerprints, because we get this tracking as the devices move around the network, we can also say, okay, let's put these fingerprints together and find the devices that are very similar to each other. And then let's kind of re-ask that question. What is it that separates this device from the devices that are most similar to each other? And so that's very generically. We actually apply that to a very wide range of types of artifacts. And we just looked at two of those artifacts in this presentation, actually. One was specifically cipher suites as it applies to a device. And the other is networks that are being communicated to from that device, where we saw the ASN example, and then that was put together to find that both in the same sessions and those network things. But the point there is, since we're constantly using the background as the baseline, that means that no, you don't have to maintain databases over time. There's no, it's just implicitly being updated all the time. And again, that was very, very intentional.
No, that's super. I certainly do appreciate that. We are coming up to the top of the hour. There's obviously a whole lot more questions out there. So I would encourage everybody on today's session to sign in next week for part 2 of this series, where you'll get some more insights and certainly some more opportunities to ask some questions about this technology. So we're right up against the top of the hour. So with that, we'd like to thank everyone for attending today. And if you'd like to share or view the recording of today's webinar, they're going to be available on Awake's YouTube channel. You can also follow us on LinkedIn and Twitter for more of our insights. We look forward to seeing you at the next Awake Security webinar, and visit us at awakesecurity.com for further details. Again, thank you, Gary. Thanks to all the attendees, and we hope to see you again next week.